I will share my iPad. And we will do our thing. All right, there it is. Okay, so now, where were we? Wait, where'd my stupid thing? There it is. Okay, so last week we were talking about the microcanonical ideal gas. Okay, and again, it's going to become relevant again today, but just to remind you, microcanonical here means that we are looking at this gas at a fixed, constant energy. Okay, and so today, what we're going to do that's new is start relaxing this assumption. But for now, let's just remind ourselves of what we got last week. Okay, so this microcanonical ideal gas is a box of volume V, where the potential outside is infinity. That is, the particles cannot escape. The potential inside is 0. Into this box, we put a bunch of molecules. Specifically, we put N molecules into this box. And again, they're all at some fixed energy E, which, as we'll show soon, is directly related to the temperature of the gas. And what we were interested in is, first of all, calculating at a given value of this fixed energy E, how many possible states, that is, arrangements of the different molecules inside the box are there. And so that was this quantity. So how many states are there? So how many states at energy E are there? Okay, and so the answer to this question was this quantity we defined called omega of E times delta E. So omega of E is the density of states. Okay, this delta E is just some infinitesimal thickness in phase space that allows us to, so this is a volume, okay, and or a distance. And when we multiply the density times a volume, we get a number of states. So this is the number of states with energy equal to E. All right, and we showed that you can calculate this by essentially integrating over all allowed values of our phase space coordinates. So these are all values where the Hamiltonian is between E and E plus delta E. Okay, so then we went through how to calculate this specifically for a microcanonical ideal gas. And we ended last lecture by answering another question with what is the probability density, which we called rho, for the first molecule of the gas to have the x component of its momentum equal to some specific value, which we called P1. All right, so in other words, what we were interested in was the probability density that the first molecule's x component of its momentum was equal to this specific value P1. And we showed how, again, since every state within this phase space has equal probability because they're all at the same energy, then this is just the subset of, well, let's not put it like that. It's the volume of the phase space subset with P1x equal to P1. And to make this normalized, then we have to divide by the volume of all phase space. Okay, and so the last couple lectures we went through this and we derived what this is. And the answer we got was this: that the probability density for one molecule in this gas to have one component of its momentum equal to some specific value was equal to this, 2 pi m times 2e over 3n square root exponent minus p1 squared over 2m times 3n over 2e. Okay, so that was the answer. All right, so now before we move on to something new, I want to point one more thing out about this answer. All right, so as we showed, this answer looks like a Gaussian, right? So the standard form of a Gaussian function is this. So it's f of x is equal to 1 over sigma root 2 pi exponent minus 1/2, no, that's no minus, excuse me, 1/2 x minus mu squared over sigma squared. So that's the general form of a bell curve, you know, this Gaussian distribution. Okay, so now if you compare our answer here to this general form of a Gaussian, you can see that what we have is a Gaussian. Okay, so our answer here, rho of P1x equals P1, is a Gaussian. Okay, specifically this value P1, excuse me, so the mean of this thing is 0. So in other words, regardless of what the value of the momentum is, it's just as likely to be going one direction as it is the other. Okay, and in particular, it has a standard deviation. Okay, and the standard deviation, if you compare it to the normal form that we have, the standard deviation is 2e over 3n square root. All right, so now what does that mean? That means that if we look at the probability density, and this is P1, then what this thing is going to look like is the following. So it's this usual bell-shaped curve that you guys are all used to seeing. It's centered around 0. Okay, and the standard deviation is the width of this. Well, so it's not, excuse me, draw it again. My undo button got a little too hyperactive there. So the standard deviation specifically is the distance from the mean out to the inflection point of this curve. So that is the standard deviation. All right, and so now notice that the standard deviation is proportional to 1 over the square root of the number of molecules that we have. So in other words, with a very large number of molecules, like we have, you know, again, we're talking about Avogadro's number of molecules, this thing is going to be extremely sharply peaked. That is, it's going to be centered at some specific value, and the width around that mean is going to be very, 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 very small. Okay? All right, so that's going to become important to us later in today's lecture. All right, so now what are we going to do today? So again, what we talked about so far is the microcanonical ideal gas. Okay, and microcanonical again means that we are at fixed constant energy. All right, so now what we wanted, so there are not many things in the world where this is true, right? I mean, just sitting in this room, for example, I am exchanging energy between myself and the room just because, you know, the light's hitting me from the window, there's some ambient temperature in the room, so I'm constantly exchanging energy between myself and my environment. And it's very, very, very difficult in order to completely isolate a system from its environment, okay? And so now what we want to do is to relax this assumption. That is, we're going to, instead of thinking about a microcanonical ensemble, you know, again, expand our minds to allow us to think about systems where they're actually able to exchange energy with their environment. All right, so what if we don't want to do this? So today we're going to say, what if energy is not fixed? Okay. And so we are going to introduce a way of thinking so in doing this, we are moving from the microcanonical ensemble to something else. And what this new system is referred to as is the canonical ensemble. Okay, so the canonical ensemble, E is allowed to vary, but other parameters of the system, for example, the volume of the box. So other parameters such as the volume of the box, the number of particles you're talking about. And I think for now, that's what we'll leave it at. These are still fixed. Okay, so the volume, the number of particles, we're going to leave as a fixed number. But now what we're going to do is allow the energy to fluctuate a bit. Okay, now, as we do this, we're going to see something very interesting happen. All right, so what we're going to see happen is just naturally in the course of trying to essentially calculate our density of states like we've done previously, what we're going to see is a function just sort of naturally fall out of the math, okay? And this function that that's just going to kind of naturally introduce itself is something called the entropy. So we're going to see the entropy just fall out of the math. And so it turns out entropy is extraordinarily important. Okay, and we'll essentially be spending the rest of the quarter talking about different properties of entropy. Okay, and so we're going to see entropy just kind of introduce itself, okay? And then after we define entropy, we're going to define temperature essentially in terms of the entropy. All right, so let's do it. Okay, so now so what we're going to do again is we're going to set up a system, okay? And we want to essentially calculate things like the number of states available to this system and the density of states of the system and calculate probabilities of the system. All right, now, at this point, the only way we know how to do this is within the microcanonical ensemble. That is, we assume all the states available to us have fixed energy, and because the probability is a function of the energy, all available states have the same probability. And so now what we're going to do in order to relax that assumption is to work within that assumption. All right, so it's actually remarkably clever. All right, so again, what we're going to do is have a system like we've had before that is a box. Okay, and again, this box is going to be completely isolated from the outside environment. Okay, so in other words, inside this box is a microcanonical system. Okay, so this is a microcanonical system. Meaning that the energy, total energy of whatever we stick inside this box is fixed at some specific value E. All right, so the total energy is fixed at value E. All right, and so hence, whatever the system is that we put inside this box, we can just throw all of our calculatory framework at it that we've already developed for the microcanonical ensemble. All right, so now what are we going to do that's different? So now what we're going to do that's different is to take our microcanonical system and just divide it into two. So I'm going to put a barrier down the middle of the box. Okay. Now this barrier is special in that if we put something like, say, a gas into the box, the molecules of the box cannot pass through this barrier, whatever it is, but energy is able to transfer back and forth between this barrier. So energy is able to be transferred back and forth across the barrier. Okay, so now what I'm going to do is I'm going to call this system on the left, I'm going to call this system 1. And the box on the right, I'm going to call that system 2. Okay, and so now we can see that the sum of system 1 and system 2 add up to a microcanonical ensemble, just like we've dealt with before. But the subsystems 1 and 2 are able to swap energy between them. And so now what we're going to do is assume that the entire system is microcanonical so that we can throw our framework at it, but then see what happens as these two subsystems interact with each other. Okay, so now we are going to assume, again, without loss of generality, you can assume other things, but you will get exactly the same answer. Okay, we're going to assume both subsystems have the same number of particles. So they both have n particles and the same volume, V. Okay, so in other words, into both of these boxes, we are going to stick a gas. And the gas that we put into each side is going to have the same number of molecules. So we're going to have N molecules over here and N molecules over here. And the volume that they have is also going to be the same. So they both have the same volume, V. The only thing they can swap between them is energy. Okay, so now, the idea is that the entire box has total energy E. System 1 is going to have some amount of energy in at E1, and system 2 is going to have some amount of energy in it, E2. And now, because the system is microcanonical, that means that the sum of those two energies has to add up to this fixed constant value. So E1 plus E2 has to add up to E. Okay, but now E1 and E2 they can fluctuate, right? I mean, E1 can have a lot of energy, E2 can have a lot of energy. These things are allowed to swap energy between one another. So only the total of the two is fixed. All right, so now I'm going to say that if system 1 has energy E1, that is going to correspond to it being in a state that I call S1. So this means, whoops. So by saying that it has energy E1, that energy E1 is going to correspond to it being in state S1. And similarly, box 2 having energy E2 is going to correspond to it being in a state, whoops, S2. All right, so in other words, if I specify the state S1 and S2 of both of the subsystems, I then have specified the state of the entire box. All right, does that make sense? Okay, very good. So now you can see that because of this assumption, that E1 and E2 have to add up to this fixed constant value of E, that E1 and E2 are coupled. Okay, so in other words, if I specify the state of one of my subsystems, if I specify what S1 is, I automatically have to know what S2 is, because I know what S1 is. I know they have to add up to S, and hence I know what S2 has to be. Does that make sense? Okay, so in other words, if we wanted to calculate, so now let's start talking about probabilities again. So let's ask ourselves, what is the probability for a state S1 to occur? Okay, so in other words, if I look just at the first subsystem, what is the probability to find it, or the probability density to find it in a specific state? Okay, so we would call this rho of S1. All right, so now because subsystem 1 and subsystem 2 are coupled, so typically we would say that this has to be proportional to the density of states that correspond to of subsystem 1 being found in state S1, right? So this is just, you know, this is as basic as it gets, or from the microcanonical ensemble, that the probability to find it in S1 is proportional to the density of states that correspond to it having state S1. Okay, but now because S1 and S2 are coupled, we can also say that this also has to be proportional to the probability of finding system 2 in some state, S2. Okay. Now, we know that essentially what the probability depends upon is the energy, right? So in other words, this density of states to find it in S1 is going to depend upon what the energy of state S1 is. And this is going to depend upon this energy of what E2 is. But now, E2 and E1 are coupled. So we can express this as omega 2 E minus E1. Okay? Okay, so let me write that out again just to be super explicit. So the probability density to find subsystem 1 in state S1 is proportional to the density of states of subsystem 2 with energy E minus E1. Okay. And this so this, again, what this is saying is that subsystem 1 and subsystem 2 are coupled to each other. That whatever subsystem 1 is doing, that depends upon what subsystem 2 is doing. Okay, now. Okay, so now let's think about how to calculate the density of states of this thing. So again, so the probability depends upon the density of states. So let's talk about how to calculate the density of states. Okay, so again, let's appeal back to what we already know. That is the microcanonical ensemble. And what the microcanonical ensemble tells us is that if we are looking at the density of states of the entire system, okay, so this is the density of states of entire system. And what we have to do is to determine the variables, or yeah, essentially what the different dimensions are in our phase space, and then just integrate over all possible values of those variables. All right, so in other words, this is going to be equal to, well, let me write, well, so you guys ought to now, let's not do it like that. So again, if I multiply this by some infinitesimal energy, then this is the number of states. And we know that the number of states is just the integral over all values of our phase space variables. Okay, so now our phase space variables now in this case, so before this, that was this, right? So we had to integrate over all possible momenta and all possible space coordinates. Okay, but now we have two sets of phase space variables. We have the phase space variables that correspond to subsystem 1 and the phase space variables that correspond to subsystem 2. And so that means that essentially our phase space now is essentially, instead of just being momentum of one system and coordinates of one system, that is like essentially two-dimensional, now it's going to be essentially four-dimensional. Right, so what we have to do, our volume element in this space is going to look like this. Okay, so this is just the phase space available to subsystem 1, and this is the phase space available to subsystem 2. And to get the volume element of the entire phase space, you just multiply all those different coordinates together and integrate over all allowed values of your phase space. Okay, and again, so again, the limits on our integral are going to be from whatever fixed energy we're interested in up to that fixed energy plus some infinitesimal amount. So now our Hamiltonian of our system is now the sum of two Hamiltonians. So it's the Hamiltonian of subsystem 1 plus the Hamiltonian of subsystem 2. All right, very good. So everybody's with me so far, I hope, yes? Okay, so let me write this again. Let me just divide by this delta E. Okay, so in other words, the density of states is this. Okay, piece of cake. All right, so now this is in terms of the phase space variables. But now what I want to do is, so this is the density of states for the entire system. Now what I want to do is to split this up. I want to essentially express the density of states of the entire system in terms of the density of states available to each of the two subsystems. All right, and what I'm going to assert is that this is correct. That the density of states of the entire system is equal to the integral over all possible values of energy 1, that is the energy of subsystem 1, times the density of states of subsystem 1, times the density of states of subsystem 2, at energies of subsystem 2 that correspond to the values of E1. Okay, so this is my assertion that if I know the density of states of each of the subsystems, then I can calculate what the density of states of the entire system is, or vice versa. All right, so now let me prove it to you. Let me prove to you that this gives you this. All right. All right, so again, we're starting out with this, that the density of states of the entire system is this. E plus delta E dP1, dQ1, dP2, dQ2. Okay. Now what I'm going to do is, so again, this little delta E is just an infinitesimal thickness that corresponds to varying our energy by a little bit. That doesn't, so E1 does not depend upon what we choose this little delta E to be. So I'm going to absorb this thing into my integral. And I'm going to rewrite this in the following way. Okay, so I still got all my subsystem 1 phase space variables here. And I'm going to associate this delta E with my phase space 2 variables here, like so. Okay. Now I have to adjust my limits. So essentially what I'm doing is taking this one big integral and splitting it up into 2 little integrals. And what that means is that I have to adjust my limits. Okay, so now I'm going to say that my limits on this phase space 2 integral, I'm going to write like this. So whatever my fixed value of the energy is, minus whatever value the Hamiltonian of system 1 takes on, which again, this value is determined by whatever this integral is. That's got to be less than the value of my subsystem 2 Hamiltonian. And it can go up to E plus delta E, again, minus whatever the value is that the first system's taken on. Now, for the integral over the first subsystem. So now what I'm going to do is, so this integral now is just over subsystem 2. This part of the integral is just now over subsystem 1. And what I'm going to do is allow subsystem 1 essentially to take on whatever energy it wants. So I'm going to say that this can go anywhere from 0 to whatever the fixed total amount of our energy is. So in other words, I let subsystem 1 do whatever it wants. Whatever subsystem 1 is doing, that feeds into this second integral to essentially to tell subsystem 2 what it's doing. And by doing that, it fixes what the limits on it are. Okay, does that hopefully make some sense? Okay, now let me erase all this superfluous. Okay, this second integral here, this is the density of states of system 2. Okay? All right, so now we just need to play with this thing a little bit. Okay, so what this says I'm doing is I have some phase space volume, okay, and I am integrating between energies equal to 0 up to whatever the total value of the system energy is. All right, so now what I'm going to do is express this in a little bit different way. I'm going to take, so in other words, this integral is over this entire possible space of energies. And now what I'm going to do is essentially to split this up. I'm going to cut it up into a bunch of little chunks. Like so. Where each and one of these little chunks has width equal to this delta E that we picked. Okay, so then what that does is that changes my limit. So instead of doing one integral over the entire space, what I'm going to do is n integrals over a bunch of little chunks. So I'm going to rewrite this as the sum over n of the integral from n delta E less than h1 up to n plus 1 delta E. Yeah, okay, and so what this says is, again, you just stick in different values of n. So for n equals 0, I'm just integrating over this first bit. For n equals 1, I'm integrating over this little bit. N equals 2, I'm integrating over this little bit, so on and so forth. And to get the total value, I then just sum all those up. Okay, so this is dP1 dQ1 times, this thing is omega 2 E minus whatever my H1 is. And that is a function of what P1 and Q1R. Okay. All right, now. So again, everybody's roughly okay with what I've done. I've taken this integral over the entire range of possible energies of my system. I've split that range up into n little bits. And then I have to sum over each one of those small integrals. And what I'm going to do is now convert this into an integral itself. Okay, and the way that you do this is that if you take the sum over some value of some function of this delta E, this is equal to, again, if I had integrated over all allowed values of E1 of whatever this function is. So again, this is integration over all allowed values of E1. So in other words, that's integration over this whole space. Whereas this is, so what am I trying to say? So I'm trying to say it's equal to this. Okay, so in other words, each one of these little integrals is equal to the sum, the total integral divided by the width of the little hunk. Okay, so by doing that, what you get is this. It's equal to dE1 1 over delta E dP1 dQ1. And now we're integrating from E1 H1 to E1 plus delta E times omega 2 of E minus E1. Okay, and now this thing, this is omega 1 of E1, right? And so what we have is that this is true. All right, so in other words, to get the total density of states for the entire system, that's composed of the product of the individual density of states of each subsystem, integrated over all possible values of the energy for one of the subsystems. Okay, so whether or not any of this proof made any sense to you doesn't really matter. The only thing that really matters is as long as you're okay with this, that the density of states of the entire system is the product of the density of states of the two individual subsystems integrated over all allowed values. Okay, so that's the painful part. So now what we're going to do is try to take this apparatus and, again, solve a problem. All right, so let's ask ourselves a question. All right, so here's the question. What is the probability density for subsystem 1 to have energy E1? Okay, so just like we did last time with the microcanonical ideal gas, we asked what is the probability density for the momentum of one molecule to have a specific value. We're asking the same thing here. What is the if we have this two subsystems that can talk to each other through exchanging energy, what is the probability that we're going to find subsystem 1 with a given specific value of the energy, which we call E1? Okay, and the answer is exactly the same as it was when we talked about the ideal gas. All right, so this probability density, which I'm going to call rho of E1, is just equal to the phase space volume, okay, with So let me call this specific value, I'm going to call that E1 star. So that's the phase space volume with E1 equal to E1 star and E2 equal to E minus E1 star. Okay, so that's the numerator. And then we have to divide by the total phase space volume. So it's just exactly the same approach we took with the ideal gas last week. We just take the subset of the total phase space that has the specific values that we're interested in. That's proportional to the probability to find it in that state, simply because all states have the same probability. And then divide by the total phase space volume in order to normalize it, essentially. Okay, so now, as we just showed here, that the probability for the system to be in the total system to be in some specific state is related to the product of the phase space volumes of the two subsystems to be in their specific states. Okay, so in other words, this thing is equal to the density of states of system 1 to have energy E1 star times the density of states of system 2 to have energy E minus E1 star. And then we divide by the total system volume. Right? So all that painful stuff we just did was simply to prove that the numerator of this should be the product of the two substate volumes. So we take the product of the two substate volumes with the specific value of the energy that we're interested in, and we divide by the volume of the total phase space. Now, notice this thing. Let me draw a box around it here. Okay, this is the product of subsystem 1 having energy E1 times the density of states of subsystem 2 having energy E2, which is equal to E minus E1 star. Notice that this is the integrand of this. Okay, so it's the integrand of this thing. So in other words, it's just the subspace volume that has the specific values of E1 that we are interested in. All right, so now let's think about what the answer to this is going to be. So again, just as we showed last lecture, we can go through some long, tedious exercise in order to get some expression for what rho of E1 is going to be. But as I tried to point out on Friday when we did this, that the argument that we're going to make is going to be very similar. All right, so what we're going to wind up getting is that this is going to be something that's proportional to 1 minus something like E1 star to the 3n minus 1 or something. So it's going to be 1 minus some very small value, or something which has to be a very small value raised to an extraordinarily large number. So in other words, what we're going to get very generally is that the probabilities are going to look like this exponent that we got previously. It's going to be some function of the energy. Okay, and this thing is going to be a Gaussian, right? Okay, so in other words, without going through the whole tedious exercise again, I'm going to tell you the answer you're going to get is going to be very similar to what we got previously. And so in other words, the answer is going to be a Gaussian centered at some value E1 star. And again, the width of this distribution is going to be inversely proportional to the square root of the number of molecules that we have. So the square root, the number of molecules we have is very, 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 very big. Okay, so in other words, this distribution is essentially going to be a delta function centered at E1 star. So in other words, you really only have to worry about one possible value of the energy, and that's the equilibrium value of the energy, E1 star. So in other words, what I'm telling you is that you let these two systems go about their business. They're going to exchange energy and eventually settle into equilibrium. And then to a very high degree of precision, that equilibrium state that they wind up in is going to be the same every single time. And the fluctuations away from that equilibrium state are going to be tiny, 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 tiny. Okay, does that make sense? Okay. So now, once the system reaches equilibrium, so in equilibrium, all right, E1 star is going to be essentially the equilibrium value of the energy that, so let me write it like this. E1 is going to equal E1 star. Okay, very precise. It will be E1 star, and the fluctuations away from E1 star will be very small. Similarly, E2 will be equal to E minus E1 star. So it'll be very precisely equal to whatever this value is. All right, so now the question is, what is E1 star? That is what is the equilibrium value of E1 and E2 that these things settle into? All right. So now again, through this argument, E1 star, our distribution, rho, so rho of E1 is very sharply peaked with its maximum at E1 equals E1 star. So how do we find where the maximum of a function is? Derivatives. All right, so we can find relationships that are valid at E1 equals E1 star by calculating this. What we want to do is to take this probability density function, differentiate with respect to E1, and set it equal to 0. And this, by doing this, this will allow us to figure out where E1 star is and how E1 star and E2 star relate to one another. Okay, everybody cool? All right, so I see that we're essentially out of time. All right, and so now so again, what we've done today is to show that this rho of E1 is equal to omega 1 of E1 times omega 2 of E minus E1 over omega of E. So this is what rho looks like. And when we come back on Wednesday, what we're going to do is to take this expression for rho and stick it in here and start taking derivatives and setting them equal to 0 and see what it tells us. Okay? All right. So does anybody have any questions at this point?
Professor, just a question on
Yes.
the standard deviation on the graph. Is it from the mean to the end of the graph, or is it from each side of the graph, the width?
The standard deviation, my recollection is that it's the distance from the mean to the inflection point of the curve.
Okay.
Yeah, so if I draw it, again, what it looks, if you have a bell curve that looks something like this, and the mean is right here, my recollection is that the standard deviation is essentially this distance from the
Okay.
mean to the inflection point right here.
Okay, thank you.
Okay, yeah. Anything else? Okay, so again, if you remember anything from today, remember this. And what we're going to do on Wednesday is we're going to start throwing this at that. Okay? All right, so until then, I will see you guys on Wednesday. Adios.